Okay, so we're going to postpone the quiz 2, and but let's pick a date later. Okay, maybe next Monday, a week from today. We'll see how we feel on Wednesday. We'll decide if we want to go for it on Monday or not. But we have a third quiz to get in there as well, and you know, there's not too many weeks left in the quarter now, so I think 4 weeks, something like that. All right, so today what I want to do is spend more time talking about classes and objects. And I know this is a big point of confusion for practically everyone. Every single person in the class, I'm sure, is confused about classes and objects. So I want to spend some time kind of going over it again, and we'll see if that's enough. We'll probably need to go over it again several times in the quarter. So let's. I'm just going to start building a program. With assignment 3 in the back of my mind here. Let's build something that probably solves assignment 3. So I have a main.cpp here. It just says bye. Yeah. All right, so here is the lighting okay, or is this too strong in the front here? Should we turn this down and move the lights back? Is that easier to see the screen? Can we try that? Yeah, let's try that. Turn these lights down here. These little ones here. Yeah. Is that better or not? Yes. Okay, good. All right. So here's the basic program. Now, let's talk about what objects are. Here's a variable x. We set it to 1. And then we can do things with it. We can print it. Let me do this. We can print the x. We can increment the x. We can print it again. So we have an object x. It's of type integer. We don't usually typically call it an object. You know, if you want to be strict in using the terminology, we call it an instance of a primitive data type. So int is a primitive data type, like an integer, single precision floating point value, double precision floating point value, bool. These are called primitive data types, and they're the building blocks of the complex data types. So a complex data type, an example of a complex data type that we've been using is string. So string is a complex data type. So if we declare a string s and set it to high, we're creating an instance of a complex data type. And we can do things with it. We can print it. We can append onto it. Oop. So we can operate on it. Here we're changing the state of s. We have a string, we modified its state. It's not a primitive data type. But when we look at the code right now, we don't see that there's that much of a difference. Actually, let me do this plus equals operation is also defined for integers, so it would look like this. So that's the same as plus plus 1. Take x, add 1 into it. Take s, append space Alice onto the end of it. So it'll say, hi, Alice. But let's do this. With the string, with a complex data type, we have functions that are designed specifically for that type, such as size. So we can print the size of S. Here's the size of S. So we define S here. It's a string, and it's initialized to hi. We print the string hi. And then we print size of S colon space, and then we print the result of invoking the function size on S. So this is special syntax, this notation here. This is called the dot notation. And so this is a function which is invoked relative to this specific instance S. It will give the size of S, so it'll print 2, right? Because S has 2 characters in it, so its size is 2. Then we append space Alice period onto S. That's adding 7. We're adding 7 characters. Now when we print S, it'll say hi Alice, and then down here once again we'll say size of S is, and then we'll print 9 because the size of S has changed. So this is the notation. This is what I'm trying to get at here. This S, we can invoke functions on there that look like this. It's the variable name dot the function name. But that notation is not available for X. X is a primitive data type. We cannot invoke functions on it like that. Let's see, let's just run this. Line 21. We forgot that. Well, we could fix the output a little bit, but here it is. Size of S is 2. Size of S is 9 here. So string S is a class. And here's an example where we create an instance of S. We can do this differently. We can make it, actually string is an exception. It has some special syntax to it. But this would be the common way to create an instance of S and initialize it to some value other than its default value, which would be empty. We could also initialize string like this. Let me comment this out here. So this is calling what's called the no argument constructor. of the complex data type string. So the string that gets created is initialized to a default value, which is the empty string, a string with no characters. So here the size of S would be 0. Let's just fix that little problem there. Let's see what that looks like. So here's the string S, it's just empty. The size of S is 0, and then we append space Alice, now the size of S becomes 7. Where's the top coming from? The 12? Well, that's that other code, X, this code here. Actually, let's take that out. I'm just trying to compare, you know, just talking about, actually, let's take that out. We don't even need that. So I was trying to illustrate the difference between a primitive data type and a complex data type. So that's one form of the constructor. Here's the other form of the constructor. This is where we invoke the constructor and pass in an argument. What's that? 2? The 2? The 2 is here. The size of S colon space, right? And then we output S dot size. So S is the string, and it's a string. This S is an instance of the string class. The string class has various functions on it. One of the functions it has is size. What are some other functions? I can't think of any. Substring. There's substring. I'll show you another function here. So at this point in the code, S equals hi Alice. So let's use the substring function and just pull out the name, the word Alice. Oops. So the substring function looks like that. So what we want to do is pull out the substring that starts in this position and that contains 5 characters, A-L-I-C-E. And it starts in the position where uppercase A is. So what position is that? Remember, counting starts at 0. So this is position 0. This is position 1, 2. This is position 3. It's the 4th position. The 4th position is position number 3. That's the one-off thing. So the substring starts in position number 3. And it includes 5 characters. But you know, I don't know, there's 2 ways of defining substring that I've seen in languages. The second argument is either the last position, the end position of the substring, or it's the number of characters in the substring. So I'd have to look it up which one it is here. Or we could just do them both and see what it does. That's let's see. So if the if the second argument represents the last position that substring occupies, then this would be position 3, 4, 5, 6, 7. That would be 7. I just don't remember which one it is. So there's two ways of I've seen substring defined in languages. I think the Java language has a different usage from the C++, I think. Let's see which one it is. It's the first one. So the second argument is the number of characters, because we didn't want the period. So this one is out. So this substring function takes two arguments. The first argument is the position of the position of the first character in the substring. That's position 3. Counting starts at 0. That's position 0. 1, 2, 3. That's position 3. That's the first argument. And the second argument, which is a 5, is the number of characters that comprises the substring. So that's 5. So here we have 1, 2, 3, 4, and 5. That's how we pull out Alice. We pull out Alice. Alice is a substring inside the string hi Alice period. This function here, when we call this, we use this dot notation. We call it against the variable s. And you can think of this as, you can think of it like this, that this whole expression here, this is invoked, it's evaluated to the string Alice, and that result is then passed into this output operator, and that's why it gets printed. So there's two things going on here. There's two activities. It's one statement, but it's not done at once. It's done in pieces. And the first piece that's done is the function substr. That function runs, and it returns a value. And the value that it returns becomes the input to this output operator. Okay, so the string is an example of a class that we have been using so far. It's a predefined class. It's part of called the standard template library in C++. When the C++ language, all languages evolve. All computer languages are changing, just like human languages. And at some point in the language, they added string. Or it may have been there from the beginning. I'm sure it was there from the beginning, actually. Okay. All right, now let's do this. Oh, one other thing I wanted to show you. That this form of the constructor, it's a bit of an exception here. Here we're creating an instance of string using the default values. You could also make it look like this. This is equivalent. This is most languages do not accept this syntax. This is a kind of a strange aspect of C++. This would be the common syntax in a computer language. Yeah.
So those 3 lines, the string s, those 3 lines mean the same thing?
Well, not exactly. This one, these two mean the same thing. And let me show you what these two here mean the same thing. So because here, these two lines initialize S to something, to high. And these two forms up here, they also initialize S to something, but they don't initialize it to high. They initialize it to the empty string. Also, these are two different constructors. A constructor is a function that you call that initializes the object. This constructor here takes no arguments. It's similar to the size function. The size function takes no arguments. This constructor here takes one argument. It's similar to the substring function here, except in the sense that it takes more than 0 arguments. The substring function takes 2 arguments. The size function takes 0 arguments. One form of the string constructor takes 1 argument. Now, the key concept to keep in mind to distinguish between constructor functions and regular functions is that the purpose of the constructor function is to initialize the state of the object that's being created. This function size does not affect the state of the object. It just reports some information about that state. So that's why we use the word constructor. We're constructing an instance of a class. We are constructing an object. We're constructing a string object. And then we use the string object. We report its size. We modify its state. We print it. We determine its size again. Okay, now what this point in the class is all about, the chapter 5, I think it is where the reading is on classes. The whole point of where we are now and what we're trying to do is to understand not how to use classes, but how to define them. How can we create our own string? Well, that's going to be too hard. So let's create our own number. Let's create a number class. And that looks something like this. Well, I actually don't want to use C out here. Then we have to implement the output operator. It gets a little messy. So let's do it like this. Let's do n dot print. So we create a number n. We initialize it to 9, and we print it. So we should see 9, right? Or we could say the number is 9. Let's see, how would we do this? How would we do this? We want this to simply print the number 9. How would we do that? Let me show you that. Now here's the hard part. This is the part you have to memorize. We define a class called number. That looks like that. The word class followed by the class name, opening brace, closing brace, and then don't forget this semicolon. There are public and private sections of a class. Oops, didn't mean to do that. Public and private sections. So what a class does, it's like a container, and we put things in it. And some of the things in the container we can look at and access, and other things in the container are hidden away. You go into a restaurant and you can access the table seating area. You can sit down and use a number of different tables, but you can't go back into the kitchen. You can't access, that's the private part of the restaurant. In the public section, normally we put the constructors, although they can also be private. The constructor looks like we're defining a function, except it has no return type, and its name is the same name as the class, and it's case sensitive. I'm using uppercase N for number, and that's a convention that most programmers follow. The class names start with an uppercase letter. Not always. I mean, string is not an uppercase S, so there are exceptions. So we have a constructor. Well, this is, our constructor has to take an integer. I'll call it I. And then it has some body in here. It has to, the purpose is to initialize. Let's look at it like that. And then we have the private section, which it's normally, this is where we hide away the things that make up the state of this complex data type. So we'll have an integer in there, and we'll call it x, number x. I wouldn't normally give it that name, but I'm going to try to avoid some confusion now by giving these things different names. Normally I would call it, I would give it the same name as this argument here. Alright, so what do we do when we create, when we call the constructor to build an instance of this class? We have to initialize the state of the class. But the class's state is essentially equal to what this integer equals. So we need to set that x to the value that's being passed into the constructor. I'll put that up there. And then we have a print function. It's a function. All functions have, we need to declare the return types. Let's print x. Just, like that. So when we call print, we just output x. So down here, we'll do the new line outside of the print function. So here we call the print function. We create an instance of the number. We pass in 9 to the constructor. See up here? The 9 goes in here. We're passing in 9. And the 9 is being stored in the private member variable x. And that this expression here creates an instance of the number class that we can then refer to that instance. From this point forward, we can refer to that instance with the variable or the name n. N is the identifier for that instance that we create in this first line. We can use that identifier here. Using the dot notation, we can invoke the print function. That's a member function of the number class. Is that all we need to do? I think so. That won't happen to you probably, right? There's no errors on there. Okay. There it is. The print function ran. The book talk about the this keyword, T-H-I-S, this. They mention it, right? I don't know if I should go into that right now or not. Now, see, this n here, let me do this. The issue that I'm thinking about is scope, okay? So when you have an identifier like n, you know, who can see the n? Well, the scope of n here is just within this. Here n is defined. And this n is then accessible for all code in main from that point forward. So here we can use n. Well, here this is a different n. That's a string literal. All right, that's just the character n. That's not the variable n. So here we're using n. Here we define n, and here we use n. Then we can't use n here. We can't do this. Well, the n is not defined in that scope. What happens if we try to do that? Well, it won't build. N, this is like this a hat, that's like a quote, I think it's, or apostrophes. N was not declared in this scope, line 13. N was not declared in this scope, line 13. I go to line 13. There it is, line 13. You can see down there, I went colon 13 for the VI people. Jumped right to the line. That is, N is not defined in this scope. They use that word, scope. What's that?
What's the difference? How can you tell?
Let me tell you how you can tell. We use these braces here to limit the scope of names. So here we created the name within those braces. So the name n here is limited to that scope. It's visible inside this block of code that's between the opening and closing braces in which it's defined. If I put the I where I put the N, like here? Yeah, if I put I there? X. Now see, that's right. So what do you want? You want to talk about X or I here? All right, this is good. X is inside these braces. This is the opening brace of the class. This is the closing brace of the class. And this member variable x here, its scope extends to the code in every function in the class. So if we were to define a new function here, x would be visible to that function. Let's do it like this. We'll do increment. This is good. X is visible in this function because this is a member function. And x is defined as a member variable. You're asking exactly the right question, so thank you very much. One after another, you're really following along nicely, and that's in fact what we need to talk about now. What is the scope of I? I is not a member variable. Its scope does not extend to all of the functions in the class. Its scope is limited to the constructor. Because I is a parameter. It's a parameter to the constructor function. And so its scope is limited to the constructor function only. So this will fail. This will fail because I is not defined there. Its scope is limited to the lines of code that appear between this opening brace and this closing brace. So let's run it again. Let's see what, I don't know what line that is. But this should be I is undefined in this scope, something like that. Let's take a look at that. There it is. I was not declared in this scope. Line 13. But X is declared. N is not declared. We looked at N already. But X is declared. Now let me reveal another possible point of confusion. Let's suppose we replaced I with N. Is this going to fail to compile, or will this compile? Everyone should make at least a mental guess and then verify your hypothesis, whether it was true or false. The issue there is that we've got an N down there, right? Well, this N represents an instance of a class, and this N here represents an instance of a primitive data type. So they have two different data types. They name two different kinds of things, first of all. But that's not the problem, actually. In fact, there is no problem. Because these two N's have a separate, their scopes do not overlap. So the compiler says, that's okay. You can have two N's in the world. And but they're separate. But they're only known in their two separate scopes. So this is okay. But what about this? Here we're defining n, and here we're defining n too. So we have two definitions of n. That's a conflict. The compiler is not going to accept this. Redeclaration of number n. Redeclaration, you can only declare it once. Declaring an object is to name its type. Defining an object is both declaring it and creating it through a constructor. A number n previously declared here, and it even gives the line number. This is similar. Here's an I'll show you. It's not specific to classes. Suppose we have an integer a which is set to 0, okay? No problem. But if we define a again and even set it equal to the same thing, it will complain. Redeclaration of int a. What happens if we did this? Is that okay? Yeah, it's all right. We're not declaring it. We're using it. We're setting it. Well, we're not changing it. We're setting it to what it already is. But, you know, so what? So this is declaring. We start with the data type, int. It's a primitive data type, followed by the name that we want to give the created object, a. Here, the data type is number. It's not a primitive data type. It's a user-defined data type. That's another term. They call it user-defined data type. It's also called a complex data type. So we provide the name of the data type followed by the identifier that'll be used to refer to that instance in the code. Okay, one more step. And this is really common, so I'm going to do this because it's so common, not in C++ but everywhere, that I want to go one step more, and pretty much you have the whole picture at that point. Let's suppose we called this thing x. Well, there's no n anymore. So here's the issue. We have a locally scoped x here. It's scoped to the function. It's a function parameter. X is a function parameter. And here, x is also a member variable. Is this going to compile? Well, you know, that would just be your guess, okay? And I'm going to guess that it's not a problem. This works. And it does work. But it doesn't do what we want it to do. These two x's here. The compiler accepted this. But this x here, okay? This x here. What x does it refer to? Does it refer to this x or does it refer to this x? Which one has more? I'm going to tell you what the rule is. The rule is if it has a more narrow scope, then it prevails. So the member variable x here has a broader scope. And this x here, which is a parameter to the constructor, has a more specialized scope, a narrower scope. And so it's this member variable x that prevails. It's the member variable x that is used by the compiler, and the more broadly scoped x is ignored.
So it starts on the inside,
Huh?
so it starts on the inside. Whatever has narrower or the most narrow scope is the one that it takes.
That's the one that it takes, exactly. And by the way, this x is also the same thing. They're both the same x. So we're taking what's in x and putting it back in itself. So this doesn't do anything. So what gets printed? When we call print, the constructor does not initialize the member variable x. So the member variable x in C++, we don't get automatic initialization. So it's just some random value, or whatever the operating system decides to initialize the memory to, that it hands over to the running program. So we allocate, an integer is 8 bytes. So we allocate 8 bytes. Is that right, 8 bytes? No, it's 4 bytes. An integer is 4 bytes. So it allocates 4 bytes, and it doesn't bother to initialize it. Just say, here's 4 bytes. You do what you want with it. That's why we need to initialize it up here to something. So this is an uninitialized code. So if we run this, what it prints is unpredictable. It's not going to print 9, right? The chances that it prints 9 are too small. There it is, a random value. That's what the memory equal. The 4 bytes has some state, and that's it. That's what the 4 bytes, when interpreted as an integer, that's its value. But this is very common. This is a good form because when you look at the code, you say, oh, it's a constructor. We're passing in x. We're just going to set our member variable x to the x that's being passed in. So this is the typical code that you will see, right, when you read other people's code. And so what we want to do is we want this x to be the member variable x, and we want this x to be the parameter x. So how do we do that? We use the this keyword. Actually, this is what's called a pointer. And we say that that's how we identify the member variable x. I'm not going to go into some details there, but this, they use the keyword this. And that's a common keyword that appears in most programming languages. So you could take this knowledge into many other contexts. Now this should print 9. There it is.
What exactly is this saying? It's saying that first
Yeah, this is,
I'm confused as to how it's
understanding it?
yeah.
Well, there's different kind of abstractions that you can make, to working abstractions, to write the code and get it to work right. And the working abstraction that I suggest that you use is that if you want to distinguish between a member variable and a more locally scoped variable, you simply prepend it with this hyphen greater than. And that's supposed to look like an arrow, okay? So if you have two names that where one of the names has a local scope and the other name is a member variable, then you can use this arrow to indicate that the name is the member variable name. Okay, that's a working abstraction that will get you to solve problems. If you want to go, yeah.
So writing this actually assigns
exactly. This is this x here. And by the way, this refers, this actually is a value. THIS is a value. It is the pointer. It's the memory address, the RAM address of the location of the object in memory. So the instance of the number class that we create here, memory is allocated. Data is stored in that memory location to store the state of this object. And this predefined word, this, resolves to the memory address of that object. So this is the address of the object. And this arrow, this is a topic that's covered in the chapter on pointers. It's like chapter 9 or something like that. And which I'm not going to get to this quarter, right? So some people try to get to it in this class and other people don't, and I can't get to it. I can't get that far, so I leave that topic out. And that's what we cover that in the next class, which is CSE202. We talk about pointers. So you don't need to understand pointers at this point. You can simply know that this is a way of, we just prepend, it's like a label. We're attaching that label to the variable x, or whatever variable we want, to say we want that to be the member variable and not the locally scoped variable that has a conflicting name. Okay, let's what are people working on now? Is it lab 6 or assignment 3? Ay, ay, ay. Do you want to debug someone's code in class now, or do you want me to go forward and look at the solution for, say, the first problem in assignment 3? Assignment 3? All right, let's look at this. So we're on our way to this. Develop a class called number. Well, we got that. That's done. We've got a class called number. We kind of got to the point where we understand that, hopefully, a little bit. It represents an integer value. Yeah, that's right. So these classes, they represent things. So you could have a class called car. You create an instance of the car, and you have number of passenger seats, horsepower, year of the make, and all that stuff. You have all that information in there packed away inside this car class. And then you create an instance of this car, and you have this abstraction. You have a car. I've got a car, and then I'll create another instance to represent a different car. So these class instances, these objects, are a convenient way of grouping together a lot of data and then sort of referring to that whole package as one thing. So we have a car. Okay, well let's invoke a function on it. Let's call calculate annual gas expense, and we write that function and we call that function, and we have 10 car instances to represent 10 different cars, and they've got lots of detailed information in it. But at this point in time, we just want to know what their estimated annual gas cost is, and then, we have a function for that, and we call it on the 10 cars. So that's the reason to use this technique in your programming. It makes it easier to organize the logic in your program, in the system that you're building. So what we have, so these classes represent things. So you sort of have to have an idea that when you design a class, what is it exactly representing? And so this number class, it simply represents an integer. The class should have a constructor that takes the integer value as its only argument. We did that. the constructor should store this value in a private member variable. We did that. Here it is. There's the private member variable. Define a public member function called isPrime that takes no argument and returns a bool. If the number is a prime number, then isPrime returns true, otherwise it returns false. Well, let's just do that right now. I mean, in stub form. In stub form. Here it is prime. Let's just return true. So every number is prime. That's wrong, right? That's wrong. But it's a stub. It's a temporary piece of code that compiles and runs, but doesn't run correctly. So let's see. What would we do? We would create the number n here. And let's call this now, like we have in the sample code, we're going to call that 9 because we're going to create more than one instance of it. We'll print it here. And then we're going to call this isPrime function. Actually, let me take this out. We're just going to call this isPrime here. So that should print true. Right? That should print true. Okay, it builds. Now let's run it. It prints 1. Okay, well 1 is, actually it's true. 1 is true. So if we return false, it'll return 0. Let's return false. Now return 0. Okay, so in C++ and C, and in some other languages, JavaScript and so on, there's 0 and false are the same thing, and 1 and true are the same thing, or non-zero and true. All right. Let's go back. So we have a little bit of running code here. And let's just paste this in there. Let's go ahead and let's get this one to work. So use the following test code. Test your implementation using the following test code. Let's just use a piece of it. Sorry. Let's use a piece of that. So we create an instance of the number class, call it 9. We want to see that is in fact not prime. And we're always returning false, so this program will be, the assertion will be okay. And here we want to do something else. Let's look at that. We want to do this. By the way, this line is not needed. That's just for people using Visual Studio in Windows. So this will succeed because we're always returning false. So 9 is not prime, it's divisible by 3. So if we call isPrime on 9, it should return false. When we return false, we negate it here. So not isPrime. So false is converted to true, and when true, so this whole sub-expression here evaluates to true. When you pass true to assert, assert just silently does nothing. It just says okay. But if we pass false into assert, assert then stops execution of the program and prints a message saying the assertion has failed. Assert was not declared in this scope. We need the Whoops. We need the header file for that. It's called CSUSB. So we need to build it. There it goes. Now it builds. Let's clear, and now let's run it. All tests passed. Oh, but if we say that 9 is prime, then we get a failed assertion. Assertion not 9 is prime failed. Gives the line number as well, line 29. So what we need to do now is to implement this isPrime function, which we've already implemented twice already. So we're going to implement it a third time. So we take our old code. We're just going to reuse our old code. But what we're going to do is, put it in this new form. So let's see how to do that. Let me see. I think I saved it from last time. Let's see. It's in temp. Is it this one? I don't remember. Oh, here we go. So we have some code to pull out. So when n is passed in here, and isPrime returns true or false. Oh, there's the code right there. Oh, I also want to put the UML class diagram in the class as well. So there it is. Oh, this is an n, this is x, right? So wherever we see an n, we need to put an x. There we go. But let me clean the code up here. There's tabs, and tabs don't work well in a lot of situations, so I like to take them out. I'm just going to take the tabs out. No, there's no tab there, right? That's a good one. This gives dividends to go through this and straighten out your code like this, because it's a way to catch errors. You just clean. I'm always cleaning, constantly cleaning, because when you clean, you catch bugs, and it's much easier. Cleaning is so much faster than debugging. All right. So we tested this code already. We're confident about this code. So let's go ahead and test it with this. It builds, and it runs. Let's get the rest of the test cases in there. Seven is prime. 77 is not prime. 73 is prime. Now, you know, actually the test code that I give is not that good. We need to test the boundary cases. For instance, 2. And this should be 2. And maybe I'll modify that on the web page. Probably we should test 3. Whoops. Wait, 3 is prime. 2 is prime. All tests passed. Wait a minute. Are we doing something wrong here? Because this is 2 is prime. So if we passed in a 4, we know that 4 is not prime, right? So this should crash, right? So if we pass a 4 in for 2, and 2 is prime, should return false, and then that'll violate the assertion. So we want to see a failure here, because, you know, it scares me to see all tests pass all the time. I want to see a failure. Let's make sure that we're running the code. Yeah, there it is, right? 2 is prime failed. All right. So there really should be 2. All right, that's that one. But there's one more, no, 2 more things to do, and we're getting low on time here. What we want to do is have the class diagram, and also breaking things into pieces. Let's get the class diagram. We'll put it in here as a header. Let me put it here. This is a multi-line comment. And we'll do something. I think I can get it from the website here somewhere. It's assignment lab 6. Okay, thanks. Yeah, it looks like this, right? And drop that in there. So this is going to be a number. And this will be the constructor. Constructor is public, that's why we have a plus sign. It takes an integer, I think we called it x. You know, that's just that name doesn't matter that much. Whoops. Gonna put a space in there too. And I think we have a print function, but I'm not sure. I think we have is prime. Let's do that. So we have is prime. We don't need the print function. Is prime is a function, and it returns type bool. It's public as well. And then we don't have any private functions, but we have a private a member variable here, and it's called x, and it's an int. So remember, the first area is the class name. The second area is a listing of the member variables, and the third section is a listing of the member functions, including the constructors. And a minus sign means it's private. It's in the private section. A plus sign means it's in the public section.
And the code that you put right now, there is a private one. Do we need it? The private X? Or that's the private there?
Say that again?
In the code,
Yeah.
at the bottom, if you scroll down, we have something under private. Is that just for the variable?
Yeah, that's the variable. This private section here, the integer x, that is shown here. That's that private and then integer x. That's how it appears in the UML class diagram. Remember, you have 2 different things. The class has got 2 different things. It's got variables and it's got functions. And we have 2 different sections in the class diagram to list those two different kinds of things. Now, as a final step, let's break the code up. So we're going to, let me copy main into number.h and number.cpp, and let me do number.h first. Here's number.h. We have the class declaration here, but we don't implement anything. I mean, we can actually, but let's. And I'm going to take the print function out. We're going to take the implementation out. I mean, for this problem, it works okay to keep everything together, but for large projects, you'll see things split like this. This is the conventional way to organize the code. So we have the declaration, and this is called a declaration. It's not a definition. A definition would provide the implementation details. We're providing what's called the public interface, well, also the private member variables as well. So these are just declared. They ends with a semicolon. There's no code provided other than those declarations. One other thing that you do inside of a header file is use this if ndef, something like this, number_h. Then we define number_h, and I know I made a mistake there. If ndef, if not defined, if number_h is not defined, then define it and include everything else that's in here. And then we have an endif on the bottom. This allows us to include the header file in multiple places, not worry about including it twice. For this problem, if you leave that out, it still runs, so that's okay. But I'm just showing you the more details here. Oh, by the way, everything that's on, you can see everything right now. If you go to my website and just type in code, I'm working on the web server, so you just pop it open here, okay? Let's go to that URL. Probably shouldn't have shown that. Everyone's just going to, it's the answer to exercise 1. Okay, let's get the rest of this. We're racing against the clock here. Here we include we have to include the number header file. We don't need to duplicate the UML class diagram. We have the number constructor. So here it is. We're going to take the print out. We don't use it in our code. IsPrime function is in the number class. See, if we don't prefix the function name with the class name, then the compiler thinks it's not a member function. And now for main, we don't need this. Here's what the main function looks like. We have to include the header file, and then we just use it like it is, see? So we have assert in here, we have cout, and now when we build it, we have to include the implementation file on the command line to the compiler like that, and then we can run it. That's it.
So the number.cpp doesn't include anything of the main function, right?
That's right. The number.cpp does not include anything on the main function. It's just the two functions, the constructor and the isPrime function.